Welcome to a lesson with Dr. Powell. Let's take a look at this complex integral. F is a function. We're going to suppose that this function satisfies the Cauchy-Riemann equations, which is the same thing as saying that the curl of f of z times dz is 0, which is the same thing as saying that the derivative exists, the complex derivative with the difference quotient. But if the complex derivative with the different quotient exists, then in particular, the quotient rule here, as long as you're in the domain away from A, this derivative will exist as well, which means that the curl of this whole differential thing is actually 0. So we'll use that in as we're computing this. In particular, we're going to let our path be this guy right here, starting from a point A and wrapping around like this, r cosine theta plus r sine theta, ir sine theta, kind of gives us a parameterization of it. Going around of a fixed radius r, we'll let r be a fixed constant for now. And then when we go ahead and replace our dz with, in terms of d theta, take a derivative with respect to theta here, we end up getting this right here. So derivative there is negative r sine theta, ir cosine theta, and a d theta. Keep in mind, this is kind of neat. Our path is like, this is a vector parameterization in two different components, the real and the complex, and the imaginary part. And if r is constant, theta is like a parameter. So in reality, this is a parametric equation, and we've just reduced it to our d. So this is kind of like our dr here, and we reduced it to a d theta, just like you would like with a dt. So we have this, and we replace our z also with this and this, and over here, and the a's cancel, you're just left with this. It's kind of neat that right in here, you can factor out an I, and you get the same thing as you have in the denominator. So you actually get cancellation, and the I will cancel with this I. You'll be left with this integral over here. Now notice we still have some dependency in R, since z is defined with an R, and z is being plugged into the function. So really we have this kind of depending on R still. Let's take a look at what happens if we choose a small r, and having that f of z is continuous, especially since it's differentiable, it'll be continuous. Then in particular, it's if you just have small variance of inputs, you have a small variance of outputs here. So your output f of z on your path as you're going around is going to be between f of a minus epsilon and f of a plus epsilon if we're fairly close to, if our input's fairly close to a. So it's going to be kind of like that. So for instance, so this integral in particular is going to be less than or equal to just integrating the bigger constant, or going to be greater than or equal to the smaller constant integrated. A constant integrated here would be very easy. Just factor the constant out. You basically have a 2 pi you're multiplying by, which would cancel out. In other words, the integral itself is sandwiched between the exact same two constants. It's also between here and here. So we can kind of think about the integral that we're considering here, z minus a with the 1 over 2 pi I is also kind of sitting in here between these two guys, between those two constants. Okay, so that means as r goes to 0, it looks like our integral, in fact, we'll be able to push the epsilon as small as we like, and it goes to, by sandwiching, it actually goes to f of a itself. And so actually in computing this, notice how I wrote an f of a here. So that's kind of the result. The result is f of a, this integral is equal to f of a, but wait a minute, that's only when r gets real small. What if r is bigger? Because this kind of depends on r, right? So to kind of offset that, we notice that if we take a bigger path for r, and so we go around it, but if we kind of then we cut in this way, and then we wrap around counterclockwise, and we go back out that way, and we go around like that. So we kind of do this this thing right here where we go here and we do that and we go back, we've actually created a loop. And in that loop, the curl is 0 all in here, inside here. I mean, maybe there's a problem at A since that's not the domain, but right in here, it's the curl's all 0. So that means that this line integral of the loop is just 0. And right here, you get cancellation going back and forth on the same path here. So what that means essentially is that that this line integral and this line integral have to be the same thing. And maybe to make that work right, though, maybe we'd have to go in and then go clockwise, probably, so it's the negative of it, and then go, yeah, that would be okay. So if we do it that way, we go in, we go clockwise, and we go around, because if we do, so then we have like a positive orientation, we have the opposite orientation. So we have like, we're adding like this plus its negative to be 0, which would mean that the two line integrals would be the same. Okay, all right. So with that little thing, what we actually get is it's the line integral is going to be the exact same no matter what r is. So Green's theorem, assuming that the curl of this guy is 0, actually tells us that this integral actually doesn't depend on r, if we think of it that way. And so even no matter what r is at all for C, it doesn't matter. It could be bigger, as long as don't have any extra domain issues to make the curl not being 0, but we're kind of in a nice neighborhood of A, that is. No matter what r we pick, in such a neighborhood of A, we'll get the exact same thing. We will get f of A. Thanks for watching.